Hello and welcome back to CS 700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. And we are talking finally about computational complexity of real data. We have discussed computational complexity, polynomial time computability of real numbers and of real functions. So let me briefly recall that before we proceed to the new aspects. So check. So here are the two definitions that we asserted but have not yet proven to be polynomial time equivalent, namely first definition for real function to be polynomial time computable in the sense of converting approximations to arguments into approximations of values. And so this definition has a subtlety that we measure the computational time only in dependence on the output precision and independently of the uh, argument and independently of the way that the argument is presented by a sequence of approximations. That was one definition. And the other definitions, which I've asserted you to be equivalent, is the conception, since we're only dealing with continuous function anyway, by considering the sequence of values of that function on countable dense sequence. So that's constitutes a real sequence, right? When we equip the countable dense sequence with a total order, such as the lexicographical order on the dyadic rationals here. So if this sequence is strongly polynomial time computable, which is a notion that I still owe you to define. And the second condition is that the function has a polynomial modulus of continuity. Whether computable or not, that doesn't make much of a difference. So, and as I said, yes, I still owe you the definition of what it means for a sequence to be strongly polynomial time computable. So this is what we're going to talk about today. So let me skip the rest of the slide about the aspects that we already discussed, namely about operators that map polynomial time computable functions to polynomial time computable function. The first operator we discussed is the join operator, the gluing operator. Whenever we glue together two polynomial time computable functions at a gluing point, which is supposed to be polynomial time computable. Well, here implicitly, we only consider the gluing point 0, which is trivially polynomial time computable. Then the function gluing together both into a larger domain is again polynomial time computable. That was our first example operator um, of a that maps polynomial time computable function to polynomial time computable functions. Our second example operator is the differentiation operator. And as you have recalled, we already know that if the derivative of the computable function has a computable modulus of continuity, then the derivative is again computable. That was a necessary and, interestingly, sufficient condition. And this characterization actually carries over to the complexity theoretic, the quantitative setting, namely if the original function is polynomial time computable and its derivative has a polynomial modulus of continuity, which is a necessary condition for the derivative to be polynomial time computable. That condition is also sufficient. It ensures that the derivative is indeed already polynomial time computable. And the proof, I'd like to remind you of the proof because we're going to use that proof later in today's session. Namely, the proof is a refinement of the proof that we use to assert the qualitative, the computability of the derivative. Namely, we use a difference quotient in order to approximate the limit, the differential quotient, and how well do we need to approximate, how close, how small do we need to make the delta. That's exactly where the information about the modulus of continuity of the derivative enters. Then if we choose this delta, then we're basically good. This will constitute an approximation to the derivative at x. It is equal to the derivative at y for some y in this interval according to the mean value theorem, but we're interested in the derivative at x. But fortunately, the derivatives at both points don't differ too much, provided that we have x and y sufficiently close. Namely, how close? That's exactly what this modulus of continuity of the derivative provides. Now let's have a look again at the complexity analysis of this, not just the computability. And the crucial part is approximating, calculating this quotient, because as you can see, the denominator is pretty close, is pretty small, 2 to the minus mu prime of n. And so the binary length of this denominator is basically mu prime of n bits in length. And that's how much it blows up any error that we incur in approximately evaluating f at x and f at x plus delta, right? So we need to evaluate x, the function f at x and at x plus delta, and we can only do that approximately, right? And how good approximations do we need? Well, we need approximations up to error 2 to the minus n, right? Because that's how precise we are asked to provide the value of the derivative. But actually, we need to approximate it better, because any error that we make here will get amplified due to the division by this very small number, which basically says it's multiplying by 2 to the plus mu of n. So this blows up the error, but fortunately it blows up the error only by this mu prime of n, and since we suppose that this modulus mu prime is polynomial, that means there's only a polynomial row up in the error, and therefore we only need to evaluate the numerator with precision 2 to the minus n minus mu prime of n, which is still polynomial in n by hypothesis. And so we evaluate it more precisely, and then this loss of precision is kind of compensated by that. Good, so that was the proof, and please keep that roughly in mind, because later in today's lecture we're going to return to that. And the third operator that we discussed that preserves the polynomial time computability was the function inversion operator. So if we take a bijective function, then there's of course classically an inverse. If the function is bijective and computable, then also its inverse is computable. But the interesting thing is the function is bijective and polynomial time computable, then of course we hope that also its inverse is polynomial time computable, but that requires some additional hypothesis. As usual, we need the hypothesis that guarantees that the inverse is again polynomial time, has a polynomial modulus, otherwise there's no chance for it to be polynomial time computable. And indeed, this is also not just necessary, but sufficient. However, let me also already here point out that it's crucial that the domain be one-dimensional. This theorem is not known to be true in dimension 2. Let me say that again. It's an open question whether, let's say, we have a function from the two-dimensional unit interval to the two-dimensional unit interval, bijective, polynomial time computable, such that the inverse has a polynomial modulus, whether this guarantees the inverse to be a Bayesian polynomial time computable or not, is subject to one of the many famous open conjectures in computational complexity theory. And if time permits, then we're going to make that statement formal later in the course of this very chapter 5, until we've characterized other complexity classes. Okay, so yes, as I said, I owe you the definition of computational complexity for real sequences. Actually, two definitions. One, strong polynomial time computability, and one about arbitrary or regular polynomial time computability. So let me briefly check here. Yes. Okay, so here's the definition, namely computing a sequence. This is to remind you, computing a sequence, of course, means to approximate any desired entry of the sequence by dyadic rationals, right? So this is our, for reminder, our standard definition for computing a sequence. And here the numerators to the dyadic rational approximations have two indices. It's a double sequence, which we can and regularly do, combined to the single sequence using this pairing function. And this is the kind of this Hilbert hotel, if you remember. And so here's the explicit expression for this Hilbert space, Hilbert hotel booking scheme, kind of. And now we refine that definition from qualitative computability to polynomial time quantitative computability. Namely, we require that the first n entries in that sequence, like we required also for computing a single real number, we require that the first n numerators of that approximating sequence of dyadic rationals must appear within a number of steps that is polynomial in n. N now not denoting the output position error, but this combined parameter, the output position parameter m and the sequence index j. So, and the natural question that arises is, how can we express that in terms of the sequence index and the precision parameter, right? This is kind of a implicit parameter, and that doesn't appear explicitly. So let's make it explicit by using some easy estimates on the value of this pairing function, Hilbert space, Hilbert hotel. Namely, the pairing of j and m is at least as large as the sum of j and m, which is easy to see from this expression. And it is at most as large as the square of the sum of j and m. And since we're interested in polynomial time computability anyway, so the difference between this and this and this is at most quadratic. It's at most polynomial, so that we can reformulate this and say that computing a sequence requires outputting approximations to the any desired entry with index j up to error 2 to the minus m within the running time, which is polynomial in the sum m plus j. And now this is a reformulation that maybe appeals better to your intuition. Okay, so to support that intuition, let me point out that this means basically running time, which is polynomial in the binary length, right? This is all classical complexity theory perception measure running times in terms of binary lengths But here in the real setting, we don't consider the binary length of the input, which is infinite. Instead, we consider the binary length of some integer output parameters. And in this case, the output parameters are precision m and index j. So which quantity has a binary length m plus j? Well, that's the unary encodings of m and j. They have binary lengths, basically m and j. So that here the running time expressed in term depends on the binary length or polynomial in the length of something. That length would be the unary encoding, both in terms of the precision parameter and the sequence index. So that's our first definition of polynomial time computable sequences. Now we already saw that there's a second definition, namely strong polynomial time computability. So what does that mean, strong polynomial time computability? Here's the definition of strong polynomial time computability of the same sequence, which begins basically the same way with computability notion, but now we require that the first n entries appear within a running time, which is polynomial in the precision parameter, m as usual, but now in the logarithm of the index. So that's the difference between polynomial time computable sequence and strong polynomial time computable sequence. The dependence of the running time in the first case must be polynomial in precision and sequence index. In the second case, polynomial in the precision and the logarithm of the sequence index. And the difference, of course, becomes significant whenever we deal with entries that have large indices. So whenever we deal with entries in the sequence that are kind of far off, right? So if there, for example, if we consider entry in the sequence that has exponentially large index, it is very far, then in the first case, that means we get a lot of time to compute that sequence because then that j is exponential. But in the second case, we only get a polynomial amount of time because here we take the logarithm of this exponential quantity, which cancels with the exponential. And so it is much more difficult to strongly compute a sequence. So that's kind of the intuition. That's why it's called strongly polynomial time computing. It's a stronger notion, more difficult to achieve that. Okay. A different way, and now expressing the same new notion, strong polynomial time computability in terms of binary length, means now we take the precision parameter still in unary as here, and as with all previous definitions, precision parameter always encoded in unary makes the dependence correspond to the binary, the length of the input parameter. But now the sequence index is here encoded in binary, because then when it's encoded in binary, then the logarithm of that index corresponds to the binary length of that parameter. So that's another way of looking at the difference between the two notions, measuring the running time in the terms of length, but in one case, the length of the precision parameter and the sequence index in unary, and in the other case, the length of the precision parameter in unary, plus the length of the sequence index in binary. Okay, and why do we introduce both of these notions? The reason is that both notions are relevant. Both notions occur, and they occur when we characterize certain other notions equivalently. So whenever we have two different definitions and they turn out to be equivalent, remember that this is evidence for these definitions to be reasonable. And we have already seen such a characterization of same thing in two different ways, namely polynomial time computability of functions. where the transformation conception was turned out to be equivalent to the dense sequence notion, where dense sequence notion, remember, that's where exactly where our notion of strong polynomial time computability arose. So the running time there must depend only logarithmically on the sequence index. Um, so that's our justification for the second notion for strong polynomial time computability. But why do we introduce the regular polynomial time computability? Again, for similar reasons, because this notion turns out to characterize some other notion equivalently. And this is what we're going to talk about on the next slide. So here's next slide. Then we talk about polynomial time computability of analytic functions. So previously we talked about polynomial time computability of continuous functions and of C1 continuously differentiable, twice continuously differential, and so on, all these functions. But now we want to talk about polynomial time computability of analytic functions. And analytic functions, as you recall, these are precisely those functions that admit local power series expansions. So that's like a Taylor expansion, but with infinitely many terms. That's a power series. And so now we have actually two natural ways of defining the computational complexity of an analytic function. First, by applying our definition of computational complexity of a continuous function, right? Any analytic function is continuous. That's our definition that we use there. And secondly, we could also define the computational complexity of an analytic function in terms of its power series coefficients, locally or globally. So two candidate definitions, and we're faced with the question, which one to choose? But fortunately, and this is where the miracle happens, fortunately, both are equivalent. So this is the definition of what it means to compute a real function as a transformation conception, and the theorem that that comes in so naturally and beautifully says that if we have a coefficient sequence Cj, and remember that capital R denotes its radius of convergence, right? So complex open disk where around zero, where this power series is guaranteed to converge, and somewhere on the boundary of that disk it will diverge. And now we go strictly inside of that disk, so we fix an arbitrary small r which is strictly smaller than capital R, arbitrary but strictly smaller. That means that the power series is defined on the closed disk with radius small r, and in particular on the real interval from minus r to r, including, and the theorem says the coefficient sequence is computable in polynomial time if and only if the power series considered as a function, as a mapping, as a transformation, when restricted to this closed unit, not unit, but closed interval, is polynomial time computable in this sense. Okay, so let me stress again that here this function and its computational complexity refers to a proper closed, actually compact subset of its original domain. Its original domain naturally is an open set, an open circle with radius capital R, and we restrict to an arbitrary but fixed proper closed subset of this domain and consider the function on this subdomain and its polynomial time computability in this sense. And this is equivalent to the coefficient sequence to be polynomial time computable. And now you see why we introduced polynomial time computability of a sequence in addition to strong polynomial time computability, because this notion indeed arises so naturally, so natural, namely in that it characterizes our regular polynomial time computability of functions restricted to analytic functions. Okay, so that's a theorem, and now let's look at the proof of the theorem, shall we? So here's a sketch of the proof, and the statement of the theorem is an equivalence. It's a two-way implication. And the first direction proceeds as follows. Since small r is strictly less than the radius of convergence capital R, there exists some real number that lies strictly between both, right? And for this real number, the very property and definition of the limit superior says that for all but finitely many of these coefficients, they grow asymptotically at most as 1 over s to the j. That's the very definition of the limit superior, right? So r is 1 over limit superior, s is strictly less. That means for all but finitely many, this quantity will be actually greater than s. And now putting things around the other way, this is a reciprocal. That means that s is yeah, 1 over s is greater than this for all but finitely many, and the finitely many exceptions can be taken care of by introducing some additive, or in this case multiplicative offset b, an arbitrary natural number. And now hard coding this parameter. Remember when we talked about computability of analytic functions, that was also the enrichment parameter at that time. And here we use that again to estimate the tail bound. So in the infinite Taylor series expansion, the power series, we would algorithmically consider the first capital J terms, where J is a natural number parameter to be chosen and fixed in a minute, and then estimate what is our tail error bound, what is our cutoff error by considering only the first capital J entries. Well, that's the rest of the sequence, all small j that are greater than capital J. And by taking the triangle inequality and using this bound on the coefficient sequence Cj, we arrive at this estimate for this tail b, this integer parameter times r divided by s. R comes from the bound that the parameter, the argument z here, or x, is at most r in magnitude, divided by s from here, raised to the j. And this is now a geometric series, right? You see this geometric series that we can bound, and it starts with capital J. So the first term is this, and then there's something that is basically independent of capital J, right? The value of a geometric series that depends on R and S, but not on J. And we want that to be smaller than 2 to the minus n in order to approximate that infinite power series, that infinite Taylor series, up to error 2 to the minus n, and we get and need to choose capital J large enough so that this cutoff error becomes smaller than 2 to the minus n. So how do we choose capital J small enough? Well, this here, R is greater than S, right? Perhaps only very little bit, but this is greater than S, no, less than S, right? R is smaller than S. Therefore, this fraction is smaller than 1, perhaps only very little bit, but it is smaller, and therefore this raising this ratio smaller than 1 to the j's power makes it indeed become arbitrarily small, tend to 0 exponentially fast. So by taking j roughly of magnitude n up to some constant factor, which depends on R and J. But anyway, asymptotically, that means that the first order of n terms, linear in n, the precision parameter, many terms of that series suffice to get approximation up to error 2 to the minus n. And calculating this requires only time polynomial in n, right? So because of this rapid convergence, that's what guarantees us that we need only to take the first linearly many terms in that series. Okay, and so that's one direction, that the polynomial time computability of the series implies polynomial time computability of the power series expansion as a function. And for the converse, so let's suppose that the power series is polynomial time computable as a function, and the claim is that its coefficient sequence can be computed in polynomial time, not in strongly polynomial time, but in polynomial time. And to prove this, observe that the coefficients can be recovered as the iterated derivatives of that function at 0, right? So C0 is the value of the function at 0. If you plug in x equals 0, then that's C0 that was recovered. C1 is the derivative of that function at 0. C2 is the derivative of that function at 0 divided by 2, right? There's a j factorial here, so 2 factorial is 2. C3 is 3 factorial times the derivative and so on. So generally speaking, the j's coefficient, Cj, is equal to j times the jth derivative of that function, iterated derivative. So our goal is to, in order to prove polynomial time computability of the series of the coefficient sequence, we're going to prove polynomial time computability basically of the iterated derivatives at 0. And this is a generalization of our previous slide, computing a first derivative of a function. Right? So that's why I kindly ask you to keep in mind our proof and estimate for computing the first derivative, because right now and here we're going to generalize that to iterated derivatives. So for the first derivative, we will use the 2 to the delta equal to 2 to the minus the modulus of continuity of the first derivative. And since here we're talking about a function whose first derivative is actually again differentiable, right? It's an analytic function. We can actually get a bound on the modulus of continuity of the first derivative by taking the maximum value of the second derivative, right? That's a thing that the modulus of continuity is related to the how steep the function is, and the modulus of continuity of the first derivative is related to the value of the next higher derivative, the second derivative. And so here we can take an explicit bound. So since the second derivative exists and it's bounded, that means that the first derivative is Lipschitz continuous, and the Lipschitz constant, a Lipschitz constant, is that maximum value of the second derivative. So that here we can choose delta to be 2 to the minus n times, no, divided actually, my bad, there's a typo here, I need to correct it, divided by the supremum of the second derivative. And now you can do the same algorithm and analysis as before to see that this difference quotient for this choice of parameter delta actually gives rise to sufficient approximation to the first derivative, computable in polynomial time. So that's what we already talked about, computability of derivatives for polynomial time computable functions. But now when we iterate that to compute the second derivative and third and so on, we need some additional property, because obviously that cannot be true in general. And this additional property is a well-known property of analytic function. And analytic function, unlike even unlike smooth function, even unlike general C infinity function, analytic function obey a certain law on their asymptotic growth of their iterated derivatives. And for your convenience, I report and remind you of that bound. Namely, if function f is analytic, let's say in the interval from minus r to r, and then if we restrict to a subinterval of half the size, just to pick some subinterval, then the jth derivative of that function on any point in that subinterval still has a power series around that point. But now the power series may have only half r as radius of convergence, right? So if we start at the endpoint of this smaller interval, then there's only distance r over 2 to the actual endpoint of the original interval. And therefore, this new shifted Taylor series has maybe a smaller radius of convergence. And on this radius of convergence, the same applies as here. Namely, the rate of convergence of these iterated derivatives is j factorial. That's a factorial from the, iterated differentiation from the Taylor series, power series, times some constant c, we had called that b in the previous slide, times r over 2 to the minus j, right? So this is expressing basically that the radius of convergence is now r over 2, at least r over 2 on this shifted point. And now we can use that and replace this estimate here with estimates about the, this was an estimate about the modulus of continuity of the first derivative, and we can replace that and generalize that to higher derivatives. So to summarize things, this analysis generalizes from first derivative to higher derivatives based on that property, on that quantitative property, that estimate on iterated derivatives. And here's a interesting first conclusion, namely, suppose we have this function which is analytic on the open interval from minus r to plus r, and polynomial time computable on a compact subinterval from small r to minus small r to plus small r. Then the derivative is again polynomial time computable. Well, we basically knew that already since we had that among the operators they preserve polynomial time computable, but its iterated derivatives are also all again polynomial time computable on this compact subinterval of the original domain. So here we have a very nice property that for analytic functions, all iterated derivatives are again polynomial time computable, and in particular, the coefficients form a polynomial time computable sequence, because the coefficients are, of course, the j's coefficient is the j's derivative at 0, well, divided by j factorial. J factorial is, of course, easy to compute. So, yes, easy to compute, let me emphasize that. The j's factorial is easy to compute in time polynomial in the precision parameter and in j. But computing it time polynomial in the precision parameter and the logarithm of j, that seems like actually an open problem. Okay, strong polynomial time computability of the factorial sequence, that's something or 1 divided by the factorial sequence, that's something we don't really know for now. Okay, second corollary is about integration. So the integral, the indefinite integral antiderivative of a polynomial time computable analytic function is again polynomial time computable on the same interval. And why is that true? Well, because since we can recover the coefficient sequence of the power series, then we can kind of integrate symbolically term-wise, right? Every single term, the integral over the jth term, for example, is Cj times x to the j plus 1 divided by j plus 1, right? So symbolic integration. And that asserts polynomial time computability of the integral, indefinite integral, the antiderivative. And the third corollary refers to maximization. So recall the maximization operator that we already talked about on computability, namely take the function and takes its maximum on all arguments up to and including x only, not beyond that. So that this is again a function, right? It depends on the upper bound of the interval over which we calculate maxima. It's a non-decreasing function, obviously. It is has the same modulus of continuity as the original function. So the question is, what is the computational complexity of this function? And for analytic functions f, we can answer that. If the original analytic function is polynomial time computable, then this parametric maximum is again polynomial time computable on the same domain from minus r to r. And the reason for that is because we can approximate the original function by finitely many terms of its power series. Finitely many terms of a power series, that's a polynomial, right? And for polynomial, there's actually, to be honest, this is a very deep property. It's not easy to prove that polynomials, the maximum of polynomial can be computed in polynomial time. The proof I have in mind for that uses Tarski's quantifier elimination, so it's pretty involved. Maybe you know a simpler proof for that, but anyway, by just using that fact, we can approximate the maximum of the original analytic function by approximating instead the approximating polynomial and using triangle inequality to take care of the error propagation, two errors. Okay, so that's some interesting properties and facts to keep in mind, that analytic functions have these nice closure properties with respect to polynomial time computability. So first is the characterization, polynomial time computability of the analytic function in terms of polynomial time computability of the coefficient sequence, not strong polynomial time computability, but just polynomial time computability. And these nice closure properties, namely the first and any fixed derivative of a polynomial time computable analytic function is again polynomial time computable on the same domain. The opposite of derivatives is antiderivative, is indefinite integration, also again polynomial time computable. And the third property is that parametric maximization is also again polynomial time computability. And all three statements and corollaries rely and use and build on approximating the original function by polynomial uniformly, that is with respect to the supremo norm. And all this only, of course, works and applies to analytic functions. A general function, even a C1 or C2 function, or even a C infinity function, cannot be approximated in general by a power series. Otherwise, it would be a power series. So it cannot be approximated well by polynomials. That's what I was going to say, uniformly, at least. Well, of course, in the average L2 sense, it is possible. But uniform approximation by polynomials, that's really what characterizes analytic function, and that's what helps us get efficient algorithm, polynomial time algorithm for these operations to instead operate on the polynomial approximation rather than the original function. But I hope, and here you ask, what about if we relax the condition of analytic function, let's say to smooth, or maybe even further to C4, C3, TC2, C1 continuous? And that's what we want to talk about in the next few minutes of today's lecture, computational complexity of operations on analytic functions and operations on smooth functions. So let's now have again a look at the computational complexity of parametric maximization, but now without the hypothesis of analyticity of the function. Instead of consider the function to be just smooth, C infinity, not necessarily a Pausers, or maybe even consider the case where the function is C3, C2, C1, or just continuous. And so let's fix such a function, polynomial time computable as always, and with modulus. And since the function is polynomial time computable, we already know that we can take a polynomial modulus of continuity like here. First thing to observe is that this parametric maximum that we talked about previously for analytic function is still computable. We know that already by using this modulus of continuity. I'll remind you that in a minute. And it's actually, this is new, it's computable in exponential time and even better in polynomial space. If you remember the complexity hierarchy that we discussed in our recaps section 4 on discrete complexity theory. So why is that computable in exponential time and even in polynomial space? Let me illustrate the algorithm more, actually even more precisely, the estimates that arise that at an example function. So consider this function as an example, and suppose we want to calculate the parametric maximum, or let's for easy convenient to say the maximum of the function on the entire interval. We already know that a function has a polynomial modulus of continuity. So when the goal is to approximate the maximum of that function up to error 2 to the minus n, what we're going to do is we're going to subdivide the domain. So this is in the codomain approximation error. And we're going to subdivide the domain, the unit interval, into steps of step with 2 to the minus mu of n, the modulus. This is what we did when we talked about computability. So this is happening here. And then we know that on each of these smaller subintervals of the domain, the function value varies by no more than 2 to the minus n. That's the whole point of having a modulus. So we can calculate the value of the function at some arbitrary point on each of these intervals, and then take the maximum of these finitely many values. And that will be an approximation to the maximum of the original function up to error 2 to the minus n for reasons that I've just explained, because although we only consider the value of that function at some arbitrary point, at a fixed one single point in each of these intervals, right? That makes exponentially many points, but the many points that we've missed in the interval, their values of the function differ by no more than 2 to the minus n because of this modulus of continuity that we use to devise and construct the subintervals. And this is an exponential time algorithm because, well, there are exponentially many subintervals, right? 2 to the mu of n subintervals of size 2 to the minus mu of n. And now the hypothesis enters that mu of n is a polynomial, so that the number of subintervals is 2 to the polynomial in n, which is exponential. That's the bad news, but which is better than doubly exponential. That's the good news. And actually, the better news is that it's a polynomial space algorithm because for each of these approximate evaluations on each subinterval, we can kind of reuse the same memory, right? So we can use uh, some memory. We need some memory to evaluate the function on this interval. And then we're going to evaluate the function also next on this interval, for which point we can reuse the original memory. We may need additional time, but we can reuse the memory. That's the essential difference between time and memory. Time cannot be reused. It's gone, it's wasted, but memory can be reused. And indeed, we need only polynomial amount of memory to store that approximate value, to store that approximate value, and so on. But we don't need to store all approximate value because only this maximum calculated so far needs to be retained and compared to the value at the next point. So to summarize, this algorithm is an exponential time, but a polynomial time algorithm harnessing the fact that we have a modulus, a polynomial modulus of continuity, and therefore only a single exponential number of subintervals. That's bad news, right? P-space is bad. Can we do better? That's an important question that every complexity theorist should ask. And indeed, we can do better, provided that P is equal to NP, provided that there's a positive answer to the millennium problem. Why is that? Well, you know that maximization tends to be NP complete in the discrete setting. So, for example, integer linear programming is a typical discrete optimization problem, calculate the maximum, and it's NP complete. Or even the Boolean satisfiability problem can be considered as a maximization problem, calculate the maximum value of that Boolean expression over all possible inputs, over all possible assignments, all possible arguments. Is that maximum 0, in which case it's not satisfiable, or is the maximum 1, in which case it is satisfiable? And that's all possible cases because we're talking about Boolean maximization. So maybe it's not much of a surprise. The surprising thing here is that apparently smoothness of the function doesn't seem to give much of a benefit. I'll return to that point in a minute. So while you think that maybe Newton method can provide for more efficient algorithm without the hypothesis P is equal to NP, while you keep thinking of that, maybe let me argue why if P is equal to NP, then actually the maximum can again be computed in polynomial time. And to this end, let us recall what it means for a function in the unit interval to be polynomial time computable. It means there exists a discrete function that provides the integer numerators to the dyadic rational approximation on dyadic rational arguments. So dyadic rational approximation to the values of the function on dyadic rational arguments. This is this restriction conception of computing a real function, means computing the sequence of values on this dense subsequence. So that means there, by hypothesis, there exists this function. This is a discrete function, partial function from natural numbers to natural numbers that provides the numerators to dyadic rational approximations to the function values of the original function, right? Add up to error 2 to the minus n, add dyadic rational arguments, more precisely, add dyadic rational arguments with a denominator 2 to the mu of n, 2 to the minus mu of n, rather than 2 to the n, because this is our modulus of continuity. So we actually need to know the argument more precisely than 2 to the n in order to have a bound on the precision of the value of 2 to the n. So this is why there's a 2 to the mu of n. And there are only finitely but exponentially many such possible arguments dyadic rational numerators to dyadic rationals of error 2 to the minus n MEDs here. And so such a discrete function phi n exists and is guaranteed to be polynomial time computable by the very definition of polynomial time computability of function in the sense of approximating rational real sequence on the countable set of dyadic rationals. And now we can use that approximating discrete function to express the original integer, the original maximization problem. Maybe let's consider the following decision problem. The set, so this is a set consisting of integer triples, which in the end will be encoded into one single integer, but let me refrain from delving into these technical details too closely. So triples, inputs are triples, n, the precision parameter in binary, in unary, which means 2 to the n in binary, recall that, and b and c, and b and c. So c is a bound on the numerator occurring as possible values of the function, right? So this is a function for 2, 0, 1. So the largest numerator when approximating the function value up to error 2 to the minus n of dyadic rational will be 2 to the n, that's RC. And the largest numerator of the argument, a divided by 2 to the mu of n, is supposed to be in the unit interval. Therefore, a is at most, b is at most 2 to the mu of n, that's our bound. And we want to know whether there exists an approximate argument and numerator a between 0 and b. That's how far we want to approximate that, where the approximate value, the numerator, exceeds c. So this is a decision problem, and this decision problem is actually a typical NP problem, as I'd like to point out, because, well, let's first look at the binary length of the argument. The binary length of the first part is n, that's how we design it. Binary length of the second part is mu of n, right? That's up to mu of n, that's a binary length. The value is up to 2 to the mu of n, the binary length is up to mu of n. And the binary length of c is 2 to the n, so that the binary length of the overall input, it's a discrete decision problem. That's the whole point. In order to make such a statement about discrete complexity classes and their relations in the hypothesis, to conclude something about a continuous problem, we need to, of course, discuss and involve some discrete decision problem. And this is a decision problem. And the input length here is roughly n plus mu of n plus n. And such a triple with this input length, so the input length is basically polynomial in n, because we know mu is polynomial in n. So n plus mu of n plus n is basically polynomial in n. And the second condition is a polynomial time decidable verifier condition, right? So this is the witness condition, whether there exists a witness of value at most the value of one of the arguments. So that in particular means that the binary length of the witness is bounded by the binary length of the argument. And the verifier condition is polynomial time decidable, because by a hypothesis, this integer discrete function is polynomial time computable. So when given a and c and n, it's easy to decide whether this relation holds, because phi n is supposed to be polynomial time computable. And here we're only comparing, we're only comparing natural numbers here, right? So all the issues about comparing real numbers that we talked about so intensively don't show up here. Well, that's why we carefully constructed all these setting and these decision problems. So baseline for now, this is an NP problem, decision problem. Now by hypothesis here, if NP is equal to P, if the millennium problem has a positive solution, then that means that this decision problem can actually be decided in polynomial time. And if this is the case, then we can actually perform binary search with respect to C, right? So we fix the precision parameter n, fix the right-hand bound for the parametric maximization, right? B is the numerator of the bound 2 to the mu of n for all t, right? So b divided by mu of n, that's approximation to the right-hand side bound. And then we wonder whether there exists an argument a that exceeds where the value exceeds c. And if we can decide that, then we can actually make binary search for c to find just the threshold beyond which the argument exceeds c, and below it does not exceed c. And this is our approximation to the maximum value, right? C is namely the numerator to the dyadic approximation of the maximum value of the function on this restricted interval. So if this NP problem actually belongs to a P, then we can have, that means there exists a polynomial time algorithm. I wouldn't know it, but they exist. And then when we can use that to perform bisection, there's no real comparison involved again. So we can just do this classical binary bisection to find the threshold value C, and that will be our approximation to the maximum value. So to summarize, maximizing non-necessarily analytic functions, polynomial time computable function, actually is pretty involved subtle question. We have boiled down the complexity from exponential time to polynomial space, and even further down to well, not really to NP, but to iterated NP for bisection. That is, if P is equal to NP, this is actually a polynomial time bisection algorithm. Okay. So this is where the famous P versus NP millennium problem enters. Now let's look at another popular problem in numerics, namely that of integration. And more specifically, we're going to investigate indefinite integration, that is antiderivative. So this is the operator of indefinite integration. Riemann integration argument is a continuous function, so that the integral is guaranteed, Riemann integral is guaranteed to exist. And we integrate that function up to, from 0 up to x, where x is now an argument, so that the result of the indefinite integration operator is again a function. It's an operator here in this setting, not a functional. We will also consider functionals on the next slide, but here we consider indefinite integration, which constitutes an operator. And we can make the same observation again in order to compute this integral. We can apply the same algorithm, subdivide the unit interval into these small items, small subintervals, such that on each subinterval, the values differs by no more than 2 to the minus n, right? That's the definition of a modulus. And then instead of taking the maximum of this exponentially but finitely many values, we take the sum over all these values, right? So scaled to the length of the intervals. So the height weighted with the length of the intervals, and then take the sum. That's precisely the Riemann sum, right? You remember the definition of Riemannian sum? That's exactly this. But now we have a quantitative statement. Riemann sum says as the width of the partition tends to 0, the Riemann sum tends to the integral. And the quantitative reassignment says, as the width is chosen to be less than 2 to the minus mu of n, as here, for modulus mu, therefore the exponentially long Riemann sum is actually an approximation to the integral up to error 2 to the minus n, which gives rise to an exponential time algorithm as previously, and more closer introspection says this is a polynomial space algorithm, because again, previously we would calculate the maximum over all these exponentially many values, and doing so by, we only need to store the current maximal value, not all values. And here for integration, we need to sum up all these values, so we need to store the sum and not all the values individually. So we can again reuse memory to arrive at a polynomial space algorithm for this indefinite Riemann integration. And again, this works in polynomial space because of the hypothesis that the modulus of continuity that governs the width and the number of subintervals is required to be a polynomial in N. So if the modulus of continuity were larger, were exponential, then we couldn't do this in polynomial space. But since we have a polynomial time computable function by one of our characterizations, we know that its modulus of continuity is at most polynomial. And again, the question, can we do better? Last time for maximization, we observed that we can do better provided that P is equal to NP. Here for integration, turns out that we can do better provided that P is equal to sharp P, which is a stronger condition because, as you recall, sharp P is a arguably properly larger class than NP. Well, yeah, to be fair, that's a lie because NP is comprised of decision problems, sharp P is comprised of functional problems, of counting problems. But remember that we're kind of a little bit generous here in this terminology. Also, let me point out that numerical folklore tends to consider maximization as a harder problem than integration. But here, on closer and rigorous inspection from the perspective of computational complexity, actually, integration has a stronger hypothesis that P is equal to sharp P rather than just P is equal to NP. And I'd like to keep emphasizing this, that real complexity theory and computer science of continuous data, that's indeed a great framework for rigorously stating and for challenging numerical folklore and myths. So numerical folklore would say integration is easier than maximization. Computational complexity theory says so far it seems to be the other way, but of course we need to really show that sharp P and NP are optimal for maximization and integration, and we'll do that in the next lecture. So here we consider not a NP decision problem, but we consider a counting problem to express the Riemann, approximating the Riemann integral in this way. And the counting problem we consider is this. So we count the number of pairs A and C in dependence on the unary precision parameter. Remember, this is unary, and it depends on the binary right-hand side parameter for the integration bound, right? So we integrate up to x, and x is approximated by b to the by b divided to the 2 to the mu of n, and we count the number of, yeah, you can look at it that way, the number of subintervals and the number of blocks in each subinterval. A is less than b, such that this is greater than equal to or equal to c. And this is a Sharpe counting problem because again, these are polynomially length witnesses, right? C has length polynomially in n, A has length at most B, and B has length polynomial in the input size. And verifying whether this holds, that's polynomial time decidable because we consider this integer function to be polynomial time computable. And since time is up for now, I have to defer the proof and argue why being able to calculate this counting function in polynomial time according to this hypothesis indeed gives rise to polynomial time algorithm for computing the indefinite Riemann integral. Also, next time we were going to look at the computational complexity of definite Riemann integration and see that apparently this could be an easier problem. So to summarize today's session, we have recalled the two polynomial time equivalent notions for computational complexity of continuous functions, of real functions. One of the two notions would involve this notion of strong polynomial time computable sequence. So I introduced the definition of both polynomial time computable real sequence and strongly polynomial time computable real sequences. And the difference was that in one case, the sequence index enters as its value, that is basically in unary in a polynomial time bound, whereas in the other case, the sequence index enters only logarithmically into the polynomial runtime bound, that is in its binary length, unary versus binary. Then we talked about polynomial time computable analytic functions, and we saw that these correspond to power series whose coefficient sequences are strongly polynomial time computable, are just polynomial time computable in the sense that I just mentioned. So both notions, polynomial time computable sequence and strongly polynomial time computable sequence are relevant, arise in our two characterizations of other notions of computational complexity for real functions. And then we talked about operators that preserve polynomial time computability of analytic functions based on symbolic operations on these power series by first recovering their coefficients, which is we know is possible in polynomial time, and then putting the coefficients back together symbolically to express, for instance, the derivative or the antiderivative, the indefinite integral, or in order to approximate the value, the maximum of that analytic function using the fact that polynomials can be maximized efficiently. Finally, we talked about computational complexity of maximization, but now not restricted to analytic functions, but restricted to arbitrary polynomial time computable function. We saw that here. The P versus NP problem would surprisingly re-emerge again, which is surprising because, again, popular belief is that in the continuous setting, it's easier to maximize. Also, we've finally concluded today's session by considering indefinite integration, where this larger class sharp P surprisingly enters. And again, this is kind of surprising and counterintuitive for numerical scientists, where popular belief holds that integration should be easier than maximization. Okay, now time is really up. That's all for today. Thanks for attending and see you next time. Bye.